Okay, this problem represents a great set of review questions. This goes back to previous units that are going to ask us about finding the midpoint, determining if lines are parallel, and verifying distances. So we have to use those three critical formulas that I harped on earlier in the quarter. So let's do our plotting. D is at 1, 2. E is at 7, 4. And F is at 3, 6. So I'll connect that so I can see what I'm dealing with. Now we know pictures lie, so we're not going to trust anything from the pictures except to give us a visual of which lines and points and what are reasonable answers. So first thing they ask us is to find G, the midpoint of DE. And if you remember, midpoint is really an average. So D2, that should be F. Oh, D to E. Yep, D to E. Remember what I'm doing there. D to E. So D to E, G is 7 plus 1 over 2, x coordinate, and 2 plus 4 over 2, y coordinate, which is going to be 8 over 2, 6 over 2, which is 4, 3. So the midpoint G is at 4, 3, and that's exactly where I want it to be. Now if I go ahead and look at H, which is the midpoint of FE, I have 3 plus 7 divided by 2 for my x coordinates, 6 plus 4 divided by 2 for my y coordinates. And so I end up with 10 over 2, 10 over 2, which is 5, 5. And that 2 ends up exactly where I want it. Now, from our review in the first part of this and our memory, if these are the midpoints, I know that I've just calculated the mid-segment of triangle FED. And this problem is really going to ask me to verify all of those properties. So which two lines are parallel? Well, pictures lie, it's pretty sure that I'm going to check the slope of HG, which is 3 minus 5, remember y is on top, over 4 minus 5, which is negative 2 over negative 1, which is 2 over 1. And the slope of FD, which is 2 minus 6 over 1 minus 3, which is negative 4 over negative 2, which reduces to 2 over 1. And if you remember, therefore my lines are parallel because the slopes are the same. Now when we look at this last part, verify that 2HG equals FD. What that's really asking us about is the distances to show that the lengths are what we know from the theorem them to be. So we are going to calculate the distance of HG. And remember the distance formula is the x's subtracted and squared plus the y's subtracted and squared. So I have negative 1 squared plus negative 2 squared. We're very careful with our calculators there. And we know here that we get 1 plus 4 because a square is always positive. And we get the square root of 5. I'm going to go ahead and leave it like that because it'll be easier to compare. So let's go ahead and do the distance of FD. We're going to find that exactly the same way. We are going to take our x's subtracted, 3 minus 1, the quantity squared, plus our y's subtracted, 6 minus 2, the quantity squared. That's going to give us 2 squared plus 4 squared, which is the square root of 4 plus 16, which is the square root of 20. Now initially, you might think you can't compare those. So we are going to take these two values and we're going to plug them in where they need to go. So we know that 2 times the square root of 5 should be equal to the square root of 20. Now I'm going to do a little fancy math. The square root of 20 is the same thing as the square root of 4 times 5, because 20 is 4 times 5. The square root has a property that lets us split it over multiplication. I still have the square root of 20, but the reason I did this is 4 is a perfect square, and so I have 2 square roots of 5 is the same as 2 square roots of 5, which I've proven exactly. We're going to do more of the simplifying of those radicals. If you went to your calculator and took 2 times the square root of 5 and you did the square root of 20, you would be about the same. Remember the rounding error, but you would be about the same and close enough to make the statement be true. So there is your